And it continues. Let's just keep practicing thinking about these things. Notice on this page, we have a new context, but still gradient vector and its interpretation, magnitude of that gradient vector and its interpretation, and then a directional derivative and its interpretation. So just a new context, but practicing computing and interpreting. So we have a temperature again. Let's see, temperature is measured in Celsius, X and Y are measured in meters, and we're at the point 1, 1. So we're at the point 1, 1, which is right here. And first, the question is just to get the gradient vector. So let's do it. The gradient vector at the point 1, 1 would be found by taking the partial derivative with respect to x at the point 1, 1, I, plus the partial derivative with respect to y at the point 1, 1, j. So as I like to do, let's come over here and work on those partial derivatives. Now, this function t is a 100 over this whole denominator, 1 plus x squared plus 2y squared. I think I'm going quotient rule. I don't really see any algebra. I could make this 100, it's supposed to be equals, 100 times that quantity to the negative 1. Maybe if you prefer that, it's fine. But I think I'm going to go quotient rule. Quotient rule says this. Take the denominator, low, d high. Take the derivative of the numerator. Now the derivative of the numerator is 0. So low d high will be 0 minus high d low. Now d low, we're taking the derivative with respect to x, and so constant, constant. The derivative with respect to x, we only have to focus on that term plus x squared. So the derivative is 2x. And then all over the denominator squared. I hope your quotient rule is still in your memory banks. We like to say it this way, low d high minus high d low all over the square of what's below, if you want to rhyme it. So really this becomes, if we could simplify, it's negative 200x over that denominator squared. Now, we are going to evaluate it at 1, 1. Thank you, author, for giving us a reasonably friendly point to evaluate at. And so what will we get? Negative 200 times 1, negative 200. 1 plus 1 squared plus 2 1 squared, 2 times 1 squared. So 1 plus 1 plus 2, 1 plus 1 plus 2, is that 4 squared is 16? So this thing comes out to be 216ths. Now I'm sure you can all plug and chug and simplify that, but 216ths simplifies to 12.5. All right, so far we've got negative 12.5 I. Now we kind of have to repeat this process for the partial derivative with respect to y. Now it's very similar because low d high is still going to be 0 minus high d low. Now the derivative of the low, 1 plus x squared plus 2y squared, that's going to be 4y. I'm just pausing to see if you track with me there. You see the plus 4y all over the square of what's below. And so simplified, we've got a negative 400y all over that denominator squared. Again, we're going to evaluate this thing at the point 1, 1. So at the point 1, 1, the numerator will be 400, negative 400. The denominator, same as before, is 16. And so you can simplify that. 400 divided by 16, I believe, is 25. So negative 25j. So there it is. There is the gradient vector. Awesome. Again, Wolfram Alpha would be happy to do that for you, I'm sure. But what is that? So here's the deal. If you're at this point and you want to move in a direction so that the temperature increases at the greatest rate, again, metaphorically speaking, I don't mean it to say at all that, hey, whenever you're on a hot plate, you should always move in a direction where the temperature increases at the greatest rate. This is just to make sense of the gradient vector metaphorically. So see if you can kind of get a sense. So 15, 30, 45, it looks like it's going by 15. So 15, 30, 45, 60, 75, 90. Look kind of to me like the heat source is there. So we should probably head, metaphorically speaking, towards that heat source directly. Not meandering, but directly. So we should probably move in that direction. Well, negative 12.5 I. So negative 12.5 I minus 25J minus 25J would definitely put us in that direction. Again, I'm not trying to get this to scale or anything. I'm just trying to get you to see a negative direction, and a negative direction is heading us towards that heat source. So it kind of makes sense. All right, now the magnitude of that vector. The magnitude of that gradient vector at 1, 1 is just going to be the Pythagorean theorem again. Because look, you've got a right angle. Let me get my pen. You've got a right angle right there. And we just want the length of that vector. And so let's do it. The one leg squared plus the other leg squared. And if you do all the arithmetic here, I've got it over here, it comes out to be 28. Awesome, 28. Don't stop there. 28 what? What does this mean? Well, the context was temperature in degrees Celsius, and the location was in meters. And so this would be an increase of 28 degrees Celsius per meter in the direction of that gradient vector. Now, the reason I put all of that is, if you're at the point 1, 1, you could go lots of directions. In fact, infinitely many directions. You could go that way, you could go that way, you can go that way. But if you go that way, that way, that way, that way, if you go any other direction, you are not going to get a rate of change greater than 28 degrees Celsius per meter. But if you go directly towards the heat source, following that gradient vector, you will get the greatest rate of change of 28 degrees per meter in the direction of that gradient vector. All right. Now, notice here, we are not going in the direction of the gradient vector. We're now going in the direction of 2 over the square root of 5i plus 1 over the square root of 5j. So if we're at the point 1, 1, and we have a positive x coordinate and a positive y coordinate, we're going that way. We're moving away from the heat source now. So certainly we're not going to see a positive rate of change, and it's not going to be the greatest positive rate of change. This is going to be a negative. This derivative here probably is going to be a negative quantity because now we're moving away from the heat source. Well, let's find out. The derivative with respect to, we're in the direction of the vector u at the point 1, 1. Here it is. It's the partial derivative with respect to x at the point 1, 1 times the unit vector. Remember, we want to scale it so it's per 1, not per something else. So when we ever, let me just back this up. Whenever we report a rate, like how fast were you driving? You would say 30 miles per hour, 72 feet per second, whatever the case may be. Which is always been my joke for 100 years now. It's an old one, but it's a joke I use. I got pulled over driving to school one day, but I don't drive to school anymore, so I never get pulled over. But I got pulled over driving to school one day, and the officer said, "Do you know how fast you were going?" I said, "Yeah, I was going 45 miles per half an hour." 45 miles per half an hour, do you get it? So we don't do that. So we scale this thing to have a unit vector direction, so it's based on a per 1 unit of time, or whatever the case may be, 1 meter, 1 whatever. So we do that thing. All right, partial derivative with respect to y times the u2. Now we've already done the legwork for all that gradient vector. Remember, this is our gradient vector. In fact, let me say it here. What we really have here is the gradient vector dotted with that vector u. Yeah, that times that plus that times that, dot product. And so that's all we're doing. So there's the gradient vector. We've already got that up here, negative 12.5 and negative 25. Let's do it. Negative 12.5 times something, negative 25 times something. Now what's the something? U is this vector. Now, based on its format, I think that's a unit vector. I think they already divided by the magnitude thing. Well, let's just check. The magnitude of U is the square root of 2 over the square root of 5 squared plus 1 over the square root of 5 squared. This thing squared would be 2 squared 4, square root of 5 squared would be 5. 1 squared, square root of 5 squared. Ah, look at that. 4/5 and 1/5 is 5/5, which is 1. Square root of 1 is 1. Yep, it's a unit vector. Good to go. So 2 over the square root of 5, 1 over the square root of 5. Now look, negative times a positive is a negative, plus negative times a positive is a negative. So as expected, this thing is coming out to be negative. And in fact, I'll let you do the computations, but I get it to be approximately 22.4 degrees Celsius per meter in the direction. I always say that because we're no longer, well, there's infinitely many directions. It's not that the rate of change is always negative 22.4. The rate of change is only negative 22.4 at the point 11 in the direction of that vector u. So what we could say is, I wrote it down over here, we could say is the temperature is decreasing at a rate of 22.4 degrees Celsius per meter if we move in the direction of unit vector u at the point 11. Get it all in there. At the point 11, in the direction of u, the rate of change is negative 22.4. The temperature is decreasing by 22.4 degrees Celsius per meter.